The next chapter that we want to work on is the chapter 36 on interference and the wave nature of light. And the first section of this is the section on linear superposition. So we're beginning now in 36.1, linear superposition. Well, what does that mean? Superposition, as it implies, means that two things are going to add up at one time, or maybe more things. And as they superimpose, like two images, one laid up on top of the other, we're saying that the superposition that we want to discuss is linear. That means it's additive in a simple way, and not in a complex or nonlinear way. The principle of linear superposition is that the resultant disturbance is the sum of the separate disturbances. Now we can see this with water waves. If a water wave is coming along here, and another water wave, maybe due to two rocks that are thrown into the water, comes along here, and as these go along, if they go to this point here, you can see that they're both saying the water should move upward. These are both what we call in phase. And therefore, the sum of what this wave would be plus the sum of this wave would be will give us the entire wave. In other words, the amplitude of one plus the amplitude of the other will be equal to the whole amplitude. Now, this goes to a much deeper level that's very, very important for physics. This is true not just for wave phenomena, but also for an electric field. If we have two electric fields, then the total electric field is the addition of those two. Of course, as their vectors there. The same is true for magnetic fields. The same is true for all of our forces that we have in nature. The gravitational and the other force, at least with the exception of relativity, all of the forces that we have simply add up. So if we have a force this way and another force this way, F2 and F1, the total force will be the vector sum of those two forces. Now, to give you an example of where that does fail and why it's important is the following. I contend to you, or suggest to you, that this is why physicists are able to know so much more about physics than other scientists know about their field. It's not because the physicists are smarter. It's because they can study the separate effects and simply add them up to get the total effect in a complex situation. This is not true, say, in sociology or in economics. In sociology, if we take a room and we put, say, a male in this room, and there are things that he can do in here, he can read books or watch TV or whatever, and we record his activity for an hour, and then we take him out and we put a female in the room and we watch her activity for an hour. Then we put both of these two individuals in the room, both male and female, in the room at the same time, and watch their separate activities. Their activities will probably bear no resemblance to the activities when they were separate. That is because the interaction between these two will be so strong that they override the previous effects, both sociologically and because one's male and one's female. Therefore, we have an extremely nonlinear situation, and the effects do not add up. So linear superposition is of the greatest importance, and it permeates all of physics, from the forces to the electric and magnetic fields to the waves that we study and how these waves add up with one another. Now, the next concept is the concept of interference. Interference is constructive if the waves are in phase and destructive otherwise. Now, what do we mean by in phase? Well, here's one wave. And now, if we look at another wave, it may start out in phase, but maybe it has a little bit higher frequency. And now you can see that although the waves are in phase here and would create a wave that's very, very large if they were added up together and go very far down here, that here they begin to interfere somewhat. And here, this wave is 0 while this is a maximum, so this is going to be not nearly as great. And then at this point right here, approximately, my diagram isn't perfect, one wave's going up, one wave's going down, so the wave would be essentially flat in this region. Then finally, flat here. Then again, as this wave is shorter, begin to become in phase again and become very large as the two waves add up together, so that you get an effect like large, not quite as large, smaller, then larger again, as these waves interfere both constructively and destructively. Here we say the phase of the waves differs by 0. Here we would say the waves differ by 180 degrees. They're 180 degrees out of phase. That's because if we think of the wave as being an angular type of disturbance, or we look at a wave, say a wave like the electric field, as E naught times the cosine of omega t plus k times x, and we look at how this wave might add up with another wave that has a different frequency and different wavelength, then we would get exactly this type of effect. We would add those two cosines up, and we'd find some places where they cancel and some places where they do not. If we look at thin films, the next descriptive thing I want to cover with you, it turns out that some strange things happen with thin films. You've all seen a disturbing phenomena of gasoline on water. So when you are going out on a lake and there are motorboats around or sailboats that are leaking some amount of gasoline, you look down on the water and a very, very thin film of that gasoline forms on the water. It is essential that that film be extremely thin, and gasoline does make a very thin film or oil on the top of water. As light comes in, it reflects both off of the top of the water and off of the next layer. As it does that reflection, there is a rather complex interaction between the two where they get out of phase, both due to the thickness and due to the fact that the reflected wave here changes the phase by 180 degrees, something I will cover later. And so the distance between these two makes this wave travel a little bit further. This is so thin that this can be of the order of a few wavelengths of light. So if we take white light coming, say, from the sun or from the sky out here, and we'd watch it as it reflects, then in fact the red can be constructive and therefore be bright, while the green, being a little bit shorter wavelength, might be destructive and get out of phase. Therefore, you would see a reddish part, a little bit thicker it'd be greenish, a little bit thicker it'd be yellow, a little bit thicker it'd be blue. And so we see this iridescent pattern due to the thin film interference with something, especially on water, when we can thin these things out. We can also see similar types of effects with a CD or a DVD, and that gives us diffraction as we look at these bands of something like this, and we look at light coming in and reflecting from these different parts of the surface. If these cuts are very, very close together, this forms what is called a diffraction grating. And therefore, when the light goes up here, it will have different constructive and destructive components depending upon where the light hit with respect to the central part. We'll cover that also, the diffraction through a slit and diffraction gratings. By slit, we're referring to having light go through, say, a pair of slits and travel at different distances, much like this, and result in interference pattern over here on the wall. We'll discuss these in detail in the next two sections.